to characterize bitumen. I will give some experimental example focusing on the viscoelastic signature using the black curve. I will explain also some work we have done several years ago to build master curve using only calculation from linear viscoelastic theory without any adjustment of curve, just by calculation. I will shortly introduce some modeling concept, and I will finish by showing a work we have done on the link between linear viscoelastic properties of bitumen and molecular structure. How we can access the molecular structure of bitumen using linear viscoelasticity. So you know that our pavements all over the world are subject to several type of loading. So of course, mechanical loading by heavy truck, which creates strain on the surface, but also on the structure. But we have also another type of constraint, which is from thermal loading by shrinkage. Of course, when we have difference in temperature across the material, we have a different type of stress created by the different dilatation or shrinkage coefficient between binder and aggregate, but also between layer. So it is very important to obtain the mechanical response of our material on our structure from low to high temperature. So typically from minus 40 degrees to 60 degrees, or perhaps more in the future. But also to obtain the mechanical response for static loading, which creates mainly routing, as you can see on the right, but also mechanical response or after high-speed loading. You know that generally the modulus increase with the speed of loading or with the frequency in oscillation. So we also know that the bituminous pavement is a multi-scale object, and we have link between this scale. This scale can be defined from hydrocarbon compound, the molecular structure of bitumen, to the structure passing through the binder, the mixture, and it's always interesting to make link between this scale between the molecular organization of bitumen and the bitumen itself, between the binder and the mixture. We know that binder is extremely important in the mixture mechanical behavior, and of course for design purpose or for monitoring, it's very important to make link between mixture and the pavement structure. And we know that the viscoelastic nature of bitumen is very important in this multi-scale approach, because the viscoelastic nature of bitumen dominates the behavior of the pavement structure. So our bitumen, it behaves like a liquid and an elastic solid in same time, depending on temperature and frequency loading or speed of loading. And this mechanical properties, this viscoelastic nature, is transmitted from the binder to the structure. So it's a key element in our type of material and structure. For that, the linear viscoelastic theoretical and experimental framework is very useful. So, of course, it is restricted to very small strain domain where we don't induce damage in material and structure, but it allows to give intrinsic properties. So it means that we can measure these properties using different tools, different mode of loading, all over the world with different equipment, and we will have the same properties, which can be useful also to be implemented in model because it is intrinsic properties. The linear viscoelastic experimental framework allows to characterize and model of material over a large temperature on loading time ranges, which is very useful to be linked to the film. We can also use this theoretical and experimental framework from the matrix, from the bitumen to the final composite, the mix and also the structure. And we have a fully developed theory and model for our bituminous material and structure. It is why the linear viscoelasticity theoretical and experimental framework is very useful for our material which is dominated by the viscoelastic nature of bitumen. So, how we characterize generally the behavior of bituminous binder. So we have two types of tests. First test is a time domain test, and it's grip and relaxation test. And the third one, oscillation, is what we call a frequency domain test. So I will choose for the time domain test the creep experiment. So the creep experiment consists in applying a stress over a certain time, here T1, and observe the consequence, the deformation over this constant stress. So you can see it is generally used in a 3-point bending mode, as you can see on the left, where we applied a stress on a bar. On this, there is a deflection, and we observe this deflection, and we can calculate the strain from this deflection. So what we get from this experiment, we get the creep modulus. So the creep modulus, I don't know if I can have the, can I show the, Ali, perhaps you know how to have a, generally I don't use,
what you want to do?
I would like to have something to show on the screen.
I think you need to share. Oh, okay. You need to change the sharing screen. Yes.
You think? No, but okay. No, it's not necessary.
No, it's still on your slide. Yes, it is still on your slide.
You can see my arrow or not?
Let me see.
I see option. Yes. Okay, yes. I have it. Okay.
Yes,
okay.
Yes, yeah. That is right. Okay.
Okay. So what we can calculate, what we can get from the creep experiment, we can get the creep modulus, which is the time-dependent strain under the stress. And you see that in viscoelastic material, the strain is time-dependent. In fact, it's a definition of a viscoelastic material. This creep modulus can be implemented in a hereditary integral, which is here, where we have the strain over time, which is dependent on the creep modulus, on the history of stress. It's the stress strain law in a viscoelastic material characterized in the time domain. And we can have the inverse hereditary integral using relaxation test, where we will have the stress over time depending on the relaxation modulus and the history of strain. So it's a way to have linear viscoelastic properties of a viscoelastic material and also bitumen. So it's used in bitumen field with the bending beam barometer, for example, in the low temperature domain. But more usual for our material, we use the oscillation mode, so in the frequency domain. And with this type of procedure, we apply a sinusoidal strain or stress, and we measure the consequence, so the sinusoidal stress or the sinusoidal strain. What we have to know, if we are in the small strain domain, so it means if you don't damage the material, the response to a sinusoidal loading mode will be also sinusoidal. It's a way to verify that you are in the linear domain. So in case of elastic material, the sinusoidal response is in phase with the sinusoidal input. So you don't have a phase lag. It's an elastic material, and in this case, the ratio between sinusoidal amplitude is the Young modulus, the conventional Young modulus. But in case of viscoelastic material, the sinusoidal response is out of phase according to the sinusoidal input, because we have a time-dependent material, and it means that we need to make the function transfer between sinusoidal input and sinusoidal output, and to make this function transfer, we use the concept of complex modulus, which can describe this relationship between the input and the output. And in this case, the complex modulus is composed of an absolute value, which is the ratio between the amplitude of the sinusoidal signal. So it's more or less the Young modulus applied to viscoelastic material. But we have also another parameter, which is the phase lag between the two signals, which is the argument of the complex modulus. And we can write this complex modulus as the ratio of the amplitude and the exponential I phi, which is the phase angle. It's a way to describe the transfer function of this sinusoidal function. So now our material in the frequency domain, we will have two parameters, the complex modulus and the phase angle. And we can measure this parameter over different frequency, because we can just change the frequency of this sinusoid, and we can measure at different temperature to characterize the overall viscoelastic behavior. There is two types of device to measure the linear viscoelastic properties in frequency domain. What we call the dynamic shear rheometer, which use mainly shear mode of loading using a plate-plate mode of loading. But we can also use dynamic mechanical analysis, and we use a lot in my lab, where we can apply also shear mode of loading, but also tension compression mode of loading, which can be very useful in the very low temperature domain, for example. So we can have the complex modulus in two forms, using the storage modulus, E1 plus E2. So E1 is the storage modulus. It corresponds to the energy stored in the material, the elastic energy. And E2, which is the energy lost lost in the material when it is loading. The other way to express this complex modulus is the norm of complex modulus here, and the phase angle. We can have two types of expression of this modulus. There is a way to pass from the shear modulus to the tension compression modulus using the Poisson coefficient. And the Poisson coefficient makes the link between the shear mode of loading and the tension compression mode of loading. So this Poisson ratio is also viscoelastic, but what we can say is that above 20 degrees, we can consider that the Poisson ratio is 0.5. So it means in the high temperature domain, we have a very simple relationship between the complex modulus and the shear modulus. And in this case, in the high temperature domain, the tension compression modulus E is 3 times the shear modulus, which is not verified in the low temperature domain. So if you want, we can come back on this. There are lots of publications on it. So what we get using a classical dynamic shearometer, or in this case, dynamic mechanical analysis. So we get isotherm of a modulus. So here I express the modulus norm and the phase angle. So according to the temperature. So I made a mistake. It's not isotherm. It's isofrequency. It's an isochrone. What we observe is that the modulus generally decreases with temperature. What we observe with bitumen. The bitumen is highly temperature dependent, and the phase angle increases with temperature. Of course, the phase angle equal to 0 correspond to an elastic material, and the phase angle reaching 90 degrees is like water. It's a Newtonian fluid. So for bitumen, we are between an elastic material and a Newtonian fluid. Concerning the frequency, more the frequency, more the modulus. It's the inverse for the phase angle. Here we have the frequency at 1 Hz and here at 80 Hz. So it is also frequency dependent, on or time dependent. More the frequency, less is the phase angle. We approaching an elastic state when we increase the frequency. So here we have the viscoelastic measurement without any treatment. But another way to observe the viscoelastic behavior of our material is using what we call natural or natural master curve, which correspond to the viscoelastic signature of our material. So on the left, we have the black diagram, which is the phase angle according to the complex, the norm of the complex modulus. And on the left, we have the cold diagram, which is another representation of the natural master curve, which is the imaginary part of our complex modulus according to the elastic part. So what we can see here, so here it's a conventional bitumen, is that the isotherm overlap themselves. You can see there is an overlapping. It means that at different temperature, we can just adjust the frequency to have the same viscoelastic measurement. When we have this unicity of curve, so here in the black diagram or in the cold diagram, we can say that we can apply or that the material obey to the time to temperature superposition principle, which is very important for our material for calculation or for modeling. So this type of viscoelastic signature could be very important to analyze our material. So here it's another black curve for pure bitumen. So what we observe is at high temperature, we reach 90 degrees in phase angle for very low stiffness. So it means that here at high temperature, so typically here 80 degrees, we are in the Newtonian domain. The bitumen is like water. It's why we can coat aggregate with bitumen, because at a certain temperature it's like water. And at the opposite, at very low temperature or very high frequency, we have a very low phase angle. We are close to the elastic state. And in between, we have a continuous behavior. We are going slowly from elastic behavior to Newtonian fluid, with a continuity of isotherm, which is important, which is due to the molecular spectra, the molecular structure of bitumen, which is composed of different type of molecular size, which represent a continuous distribution. It is very important. And we observe that this black curve passed from 45 degree of phase angle. On 45 degree, it's an interesting point, because it means that we store the elastic part is equal to the imaginary part. We store energy at the same level as we lost energy. But what you have to understand is that we have a continuous curve, and once more, it means also that this material obeys to the time to temperature superposition principle. So here I show you the black diagram measured on a polymer modified bitumen. So we just add 5% of styrene, butadiene styrene in a usual conventional bitumen. And what we observe is that the linear viscoelastic signature is different from conventional bitumen. We have what we call an elastic plateau here. It means that the polymer give elasticity to our material, and we can observe this with this elastic plateau. And of course, we are still elastic at low temperature or high frequency, and we are approaching the Newtonian state at high temperature. But what we have to recognize is this elastic plateau given by the addition of the polymer. Here I show you some black curve of aged bitumen. And what we can observe here in the black diagram, so in the low temperature domain, we are still elastic, and in the high, we are approaching the Newtonian state. But in this case, the isotherms don't overlap themselves. So it means that the viscoelastic signature is not the same from a temperature to another. There is something which happens in the material with temperature, which is not the same at different temperature. We can imagine that there is some phase separation inside. It could be also due to some wax crystallization or wax melting. It could be due to several chemical physical aspects, which lead to phase separation in the material. The material is not the same from a temperature to another, and we can see this behavior on this black diagram, which is very important. This, for example, this edge material show an instability from a temperature to another. Another case is a biobinder. So we can see in this case that the unconventional viscoelastic signature on another material, which here it's a biobinder, and we observe also an elastic plateau, and we observe also that at low temperature we behave like an elastic material, close to an elastic material, and we reach in this case here 70 degrees, not 90 degrees. So in the previous example, we see that we have material, we behave like a thermoplastic material, so it means they melt and they tend to reach this Newtonian liquid at high temperature. But if we measure this linear viscoelastic material on thermoset resin, like here on polyurethane, we see a viscoelastic signature, very different. So in this case, at very low temperature, we behave like an elastic material, like bitumen, but at high temperature, the phase angle tend to very low value. So it's due to the cross-linked nature of the molecular structure of thermoset resin, which this thermoset resin doesn't melt, in fact, due to the cross-linked structure, and we can see it on this black diagram. So after this example showing the importance of the black curve, the black diagram to understand our material, I will try to explain a method to build master curve from only calculation. So building master curve is working only for material which obey to the time to superposition, time to temperature superposition principle. So it means on this norm of complex modulus to adjust the isotherm on a curve, using a reference temperature by translating the curve horizontally on a theoretical curve, which allow to have access to a frequency non-measurable by some experiment. So we need to find this translation coefficient. So according to temperature, this translation coefficient is depending on temperature. So for that, we can use what we call in the viscoelasticity theory the causality principle. So the causality principle is defined in some relationship defined by Kramer-Kronig. And this Kramer-Kronig relationship is true for function meeting the Boltzmann superposition principle. So, or on another way, the time to temperature superposition principle. So here we have the equation of this Kramer-Kronig relation. We have several types of relation, but it is one of this relation which link the phase angle to the norm of complex modulus and also the frequency. Budge and Toon, several years ago, make an approximation of this Kramer-Kronig relationship and give this approximation, which shows that the phase angle. So here you see the phase angle. What is the phase angle? In fact, the phase angle is the ratio between the derivative, the the phase angle is a derivative of the log of the norm of the complex modulus across the log of the frequency. So in fact, there is a strong link between this slope here, the slope of the norm of complex modulus, and the phase angle. In other words, the phase angle, what is the phase angle? Is the slope of the complex modulus across frequency. And we can use, so just before, we can verify, and I invite you to verify on your linear viscoelastic data. You will see that it's worked very well, and if it doesn't work, it means that perhaps you have a problem with your measurement. So here, I put the derivative of the log of the norm of complex modulus according to the phase angle, and you see that we have a line. It is verified, and it is verified on linear viscoelastic measurement on bitumen, but also on mixture. And it's generally verified. So we can use, after the verification of this relationship, we can use this relationship to access to the translation coefficient to construct master curve. So I invite you to read a paper we have. I have the reference at the end of this presentation. We can, by some mathematical transformation of the Budge-Thun relationship, access to the translation coefficient. We can calculate from the phase angle we have measured and the norm of complex modulus we have measured. So we measure only this parameter, and we can have access to the translation coefficient, and we can, using this this way, we can calculate just by calculation without any adjustment of curve. We can calculate the master curve. So here I show you some master curve, and you can see that this master curve are very smooth. Perhaps not very smooth for the phase angle, but perhaps there is a reason. If you want, this master curve construction is implemented in a software available on internet, and the address is here, Viscoanalyse database start.fr, and you can use it to calculate master curve using this this method. Concerning the modeling, so we know that there is lots of type of modeling, like the generalized Maxwell model or Kenville model or other type of model, but there is some interesting model using a special dashpot, which is non-linear dashpot, in fact. This dashpot behave between a spring and between a linear dashpot. You can see the expression here of this frequency response of the model. And this model, using this non-linear dashpot, is very useful to model the linear viscoelastic properties of bitumen, but also of mixture. They have been developed a lot here in France, in the Gustave Eiffel University, but also at the ENTP school by Hervé Di Benedetto and team. And you will see here that this type of model, so here is this one, allow to perfectly model the linear viscoelastic properties of bitumen, and you can verify in both the black diagram, but also in the cold diagram. So now I will finish by the last section of this presentation, showing how we can make the link between the molecular structure of bitumen and the linear viscoelastic properties. So we all know that the bitumen can be considered as a structure material with a continuous molecular mass. You remember the black curve, which is continuous, which shows that we have a continuity in molecular mass in our bitumen. So from very large molecules, generally called asphaltene, to small molecules, so saturate molecule. You can see here size exclusion chromatography spectrogram on the wall asphalt, wall bitumen here in the dot line, but also the spectrogram on the asphaltene, which correspond to higher molecular mass, the saturate, which correspond to the lowest, and the intermediate fraction, the aromatic, and the resin. And you understand that the bitumen is composed of all these fractions, the blend of all these fractions, which give an average molecular distribution. So we can use this this molecular continuous structure to make the link between the linear viscoelastic measurement and the molecular structure. For this, we use what we call the delta method concept. It is a method strongly developed for fusible polymer, for thermoplastic, for polyethylene, for example, other type of polymer. And this method had been introduced by Zanzotto several years ago for bitumen. At this time, they use the norm of complex modulus, but we have adapted the method in the Andrea Temelli doctoral work. And this method is based on the observation time, which is the inverse of the frequency, versus the molecular relaxation time. So what means the molecular relaxation time? This relaxation time means the time to a molecule to come back to equilibrium after a loading. So it means that you destabilize a molecule, and the molecule tends to come back to the initial state, and the time to come back to the initial state, it's called the molecular relaxation time. And of course, this concept is based on the observation time and the relaxation time. If you observe at a very short time, you don't see the equilibrium, in fact. And if you observe at a very long time, you will see nothing, in fact, because you will just see that the molecule is at the equilibrium state. So we have adapted this concept using the phase angle master curve, because we think the phase angle master curve is very useful for this. So you see here that at a very low frequency, we are in the Newtonian domain at 90 degrees, and at the very high frequency domain, we are in the elastic state, and in between, we have a continuous curve showing a continuous size molecular distribution influence on the phase angle. In the high temperature domain, the response, the linear response, is influenced by the biggest molecular structure, and the biggest molecular structure have long relaxation time. It's what you know from polymer science. So the phase angle reach 90 degrees, and we can consider that the phase angle reached 90 degrees when the observation time or the inverse of frequency, is very long compared to the longest molecular relaxation time. At the opposite, in the low temperature domain or the high frequency domain, we are very strongly influenced by the smallest molecular structure which have short relaxation time. So we can say that the phase angle reach 0 degree when the observation time is very short compared to the shortest molecular relaxation time. So knowing that, knowing that we have a continuous curve here, with a measurement at decreasing frequency, we have more and more molecules of increasing mass which relax. So they don't relax. So it means that they don't contribute anymore to the mechanical response. So we understand from this curve on this explanation that the phase angle is linked to the cumulative molecular weight. It means the cumulative weight of fractions of species up to a specified molecular weight. So how we will use it? We will make some assumption. We will make the assumption that the cumulative molecular weight distribution curve is proportional to the phase angle master curve. The Bituminous in the polymer ion has made the same assumption. And we will use the relationship between the crossover frequency, which has been measured at 0 degree, on the molecular weight, and which has measured by Zanzotto. We have the link between the molecular weight and the frequency. And using these two curves, we can measure the molecular distribution by differentiating the phase angle in fact. So the method, firstly, use modeling. And for this modeling, we use this type of modeling with two non-linear dashpot and one linear dashpot. And you can see that the model perfectly fit the experimental curve and allow to have access to this extreme behavior at very low frequency and very high frequency, because we need to access to the 90 degree of phase angle and to the 0 degree of phase angle, and by extrapolation, in fact, on this model allow to access to this extrapolation. So the method consists of measuring the complex modulus, building the master curve, calibrate the model, transform the frequency in molecular weight using the Zanzotto relationship, and then to differentiate the model phase angle master curve, in fact, and we just get this molecular distribution. Here, these molecular distributions are calculated for a very hard bitumen on several bitumen of different penetration grade from 1020 to 5070, and you can see that the harder bitumen have the highest molecular weight, and the soft bitumen 5070 have the lowest molecular weight. So we rank our binder according to the consistency measured by the penetrability. So it's a good thing. If we compare the result of this delta method to the usual size exclusion chromatography method, so the method is here. Here we have the size exclusion chromatogram, Here we have the chromatogram measure using the delta method. So of course, we have not the same distribution, but the good news is that this distribution is centered around the same molecular mass. It means around 1000 Dalton. And we rank our material on the same way. But of course, the distribution is wider using the size exclusion chromatography method in comparison to the theoretical distribution calculated from linear viscoelastic measurement. It's why we call this distribution apparent distribution. It's an apparent distribution coming from the linear viscoelastic measurement. I will show you some examples of the use of this delta method. So, for example, we have measured this distribution on an asphaltite. So, asphaltite, the hard bitumen, is solid at room temperature. It contains some fraction, mineral fraction, and you can see that the distribution shows very high molecular, high molecule. And when we blend this asphaltite at some percent in usual bitumen, we recognize that the distribution go to the highest molecule. It's a way to understand what's happened when we blend heavy molecule material in a usual bitumen. What's happened? How the dispersion is made. At the opposite, when we add to very old bitumen rejuvenator, we can also observe that the distribution goes to the lowest molecular size, and we can understand what's happened when we add a rejuvenator or other type of oil, light oil in bitumen. It could be useful to understand blend, for example. So I will finally show you how we can use this delta method to define a criteria related to the cracking properties of bitumen. From the Siroma Rodrigo doctoral work, we have defined a special frequency on the phase angle master curve from statistical study, and this frequency, it's a typical point where the phase angle across aging show something which happened on the phase angle curve. And it is interesting to note that using the Zanzotto relationship between the frequency and the molecular weight, this molecular weight corresponds to 1500 Dalton, which is more or less 2 times the asphaltene molecular size. So it's why we think this frequency corresponds, when we transform it in molecular weight, in an agglomeration of asphaltene. And we know that aging of bitumen, which leads to a more cracking behavior of bitumen, it is dependent on the agglomeration of asphaltene. And so we can define, we can see on the bitumen, a fresh bitumen, on the aged bitumen here, using RT40 on PAV, that a new population appear after aging, using the delta method, and this new population arrive in the high molecular size domain, and we imagine that it represents some molecular agglomeration, molecular asphaltene agglomeration. So we can use the delta method, the distribution calculated with the data method to define a new criteria, which is the molecular agglomeration index, which corresponds to this area in percentage. And we have measured this molecular agglomeration index. So according to lab long-term aging, so in this test, it's age using the Riley method on asphalt, and we can see that this molecular agglomeration index increased according to aging, and we have compared this molecular aging index with the conventional, very used Glover-Rowe parameter. It's very close to the Glover-Rowe parameter, but the advantage of our molecular agglomeration index is that it shows a better reproducibility. This means that we can calculate in different places using different dynamic shearometer, and we have a better reproducibility with this molecular agglomeration index. We have also compared this molecular agglomeration index with the fracture temperature using the TS-RST test on mixture, and we find very good correlation, very good evolution of this molecular agglomeration index according to the fracture temperature, and there is it seems there is a limit where the phenomenon of fracture temperature accelerates at a certain molecular agglomeration index close to 0.6%. It corresponds perhaps to the gelification phenomena with asphalt. So, in conclusion, I show you that the linear viscoelastic theory framework could be very well adapted to understand the bituminous binder material behavior, but also alternative binder material. It is interesting because we have a direct link with this linear viscoelastic behavior between mixture and structure. So it could be very interesting for the final object, which is the pavement. I also show you that we can calculate master curve using just a calculus coming from the linear viscoelastic theory. And we can use also this viscoelastic measurement to access the apparent molecular distribution. And this apparent molecular distribution can be used to calculate an interesting promising parameter, which is a molecular agglomeration index, which can be related to the quality of bitumen. So here I have some bibliography I can give you, and I just want to make an announcement. We organized with some researchers all over the world the second international workshop on the use of biomaterial in pavement in Sao Paulo, Brazil, in next September. So it will be on site, but also online. So we will be very happy if you can participate. So thank you very much.
Okay. Well, thank you so much, Emmanuel, for your presentation. Very insightful, very informative, and very interesting. And current research. Thank you so much. I know it's the research that you are doing for some time on that, and it's very interesting, the latest development and advancement in the research that you are doing. Okay, with that, I think we can go to the next session, which is Q&A session. I would like to ask if among our audience, if anyone has any question, please raise your hand and turn on your mic directly, or type your question in the chat box, and I will read the question.
People are shy.
Okay. Yeah. So, okay. So, Haibo, yes, please.
Okay. Sorry. Thank you, Professor Emmanuel. Very good presentation. And I have one simple question. Like for your DSR, did the DSR at -10, if I remember, like the temperature is -10. So you use 4mm DSR or 4mm plate, like plate, or just a regular 8mm, like.
So very interesting question. In fact, in my lab, we don't like dynamic shear barometer for low temperature, because we know that at low temperature, the stiffness of the dynamic shear barometer itself will play a role. But of course, if we can't make, with another device, we will use a dynamic shear barometer. For me, at -10 is not really a problem if your device take into account the stiffness of the barometer itself. I never tried, in fact, the 4mm, but what I know is that the sample preparation is very difficult. But so what I can answer is that for low temperature domain, we use the DMA, in fact, the dynamic mechanical analysis, and we use in tension compression mode. Yes.
Okay, thank you. Yeah.
Yes, so we use a special. There are different type of dynamic mechanical analyzer. So I can give some mark from. No, but here we use a typical French device, which is a Metravib apparatus.
Okay,
That's special, strongly used to measure polymer behavior. So
okay,
for me, the dynamic shear barometer is a problem for low temperature.
That's right.
Thank you.
Good. Okay, thank you, Haiba, for your question. Thank you, Emmanuel. Other question among our audience?
So
okay.
What can I say? If you have some question and you are too shy to ask question, no, you can send me email and I can answer.
Yes, okay. Of course. Yes, this is the thing that they can, of course, send their question. I also have, Emmanuel, one question about the sensitivity of the model, the linear viscoelastic model that you develop. The theoretical model. How is it sensitive to the type of the binder? I mean, I'm talking in terms of the petroleum-based bitumen, and what we are hearing recently about the plastic-based bitumen, or these new types of bitumen, or non-petroleum bitumen. How this have you done any research or the experiments or lab tests to see really what is the different response if we get from the non-petroleum bitumen?
So first, what I have to do is this type of model can be only used if you have viscoelastic, the thermal simplicity. If your material obey to the time to temperature superposition principle, and we know when we add some plastic waste and some other type, sometimes you will see on the Blake diagram some different things, and perhaps we cannot apply strictly the model. In fact, so we have to be careful when you apply the model that the model obey to that it's not always useful to use a model. In fact.
Okay. Okay. Great.
Or you lose some precision. You lose some. Yes. I think so.
Okay, great. That is the point. Okay, great. And okay, any other question? Okay. So I also have also another question about the delta method and MIA index, which is very interesting, and how to connect the molecular structure of the asphalt binder with the linear viscoelastic behavior of asphalt binder material. So, and as you mentioned also in your the presentation at the end of in your conclusion. This is the connection for the next steps, which is going to a mixture level and the structure design of the material. How we can since all the scale and the phase that you studied was in the binder level the phase. So I want to know if whether you try the further this research into whether mastic level or mortar level, and to see really this rules or is applicable to also to the higher level, or no, we just need to stick into the binder level. And yeah, I want to know your insights about this.
Yes, it's a good question, in fact. So at the moment, the model is restricted to non-modified bitumen. So the next step on, I know that some researchers are working on that, is to adapt this model to adding elasticity in the material. In fact, so we need to adapt this model first for polymer modified bitumen, but in this case we need to add another object, which is the polymer. So when we add a polymer, we have not the same continuous distribution, in fact. So we have to understand, and we have to work on this subject to add on the model this type of particle, which could be useful also to pass to the other scale, to the mastic scale. Yes, it is something we need to do. So at the moment, I'm not working strongly on that, but we should do that. So if you have time.
Yes. Okay. Thank you. Yes. Okay. Great. Thank you. Thank you, Emmanuel. Okay. Other question, Emmanuel? It seems. Okay. We don't have any other question. So thank you so much, Emmanuel, for your the accepting again for my invitation, for your very insightful presentation. And thanks to audience and everyone who attended this webinar. I think before we wrap up our today webinar, I'm wondering, Emmanuel, about the last message I sent you through the LinkedIn. If you have time, we can have some conversation or discussion about the some mutual work or research.
Mutual visit. Yeah.
Yeah, mutual visit.
Yes,
and
yeah.
Okay, let me check with the international office here at the Université Gustave Eiffel, because I know that we are involved at the Université Gustave Eiffel in some international project. Before to answer, I need to speak with the international officer here at the university.
Okay. Okay, great. That would be great. We are really looking forward to the hopefully seeing you in Chengdu in future and host you in face-to-face. And I don't know, have you had a chance to visit China? I hope we can host you in future, and I hope that through this kind of bilateral collaboration, research exchanging, that we can find the more opportunity for collaboration, joint research, and publication. Yeah, this is something that we are looking forward. My colleague and Haibo, Dr. Din Haibo, and myself.
Thank you.
Okay, thanks a lot.
Thank you.
It's the same. Huh? If you are in France, don't hesitate to come here in Gustave Eiffel University. We are located in different places all over France. Myself, I'm in Nantes, in the west part of France.
Okay.
2 hours by train from Paris.
Okay, great. Thank you. Sure. So we are looking forward anyway. So thank you so much again, Emmanuel. Thank you, everyone. And this is the end of our today webinar. I hope everyone get the lot of information and from this presentation. And again, thanks to Emmanuel for his time. Okay, so with that, we wrap up our today presentation and say bye to everyone. Thank you, Emmanuel. Thank you, Emmanuel. Thank you, everyone. Bye. Bye. Have a nice day.